So in last lecture, we have introduced some protocols at the application layer and also at the in between the application layer and the transport layer. There's a TLS/SSL. And first, let's recap what are the key points of TLS. I hope you remember something. So recap of TLS, or we say SSL. So first of all, do you remember what are the security services provided by TLS or SSL? Do you remember? Source port? No, that's not about the security services. Encryption, handshake protocols. Yes, that's good. So in general, this protocol is for security purpose, and it enables secure communication. By secure communication, we mean that it provides two fundamental security features. One is authentication, and the other one is confidentiality. So it means that when the client use TLS to communicate with a server, then their communication traffic, like the data, the content of their communication, will be encrypted. And also, there will be message authentication code in the place to provide integrity of the data. That's true. This authentication, in fact, it has two means. One, let's talk about the data integrity. Data itself, its integrity. And also, when it refers to who is talking to whom, then it has this entity authentication or data origin. That's better at the moment, data origin. Then it has this long repudiation, repudiation. And since this data origin can be assured by the signatures from the sender, these signatures was generated based on the private key of the sender. So then another important thing is, so for integrity and confidentiality, it requires the two communication parties to share secret information and also to make sure the data is sent from the other party. So how can we be sure the data is really from the other party who claim to be? And then we use the public key certificate. In fact, issued by certificate authority. That's X.50 line. Pub certificate, pub key certificate. So with this public key certificate, then the two communication parties, especially the client, can verify the data origin from the server. And also based on this, they can share secret keys. And after that, they can use this key as input to generate session keys for message authentication codes and symmetric ciphers. So that's the process. And now let's move on to what? Let's move on to the lecture about the Tor network. Before that, last time I have gone through some of this internet privacy very quickly. I'm not sure whether I have explained it properly. So let's go through it one more time. It's I consider it more interesting to you for us end users. And there are a lot of elements in this topology, very basic. So for example, in the very beginning, it's also like a recap what we have learned from previous lectures regarding network security. So in general, like we have a user and we have a server. Suppose the user wants to visit some web pages maintained by the server. And mostly, especially in the organization network, there will be a firewall set up at the gateway router. And this firewall will be able to see the source IP address, that is the user, and the destination IP address on the user's request. And this data, in the context here, we assume the user wants to fetch a web page from the server. So the data itself, it's HTTP data. So when this file is enabled, then the file will be able to see the source IP address and the destination IP address. It means that the user cannot hide from the firewall that it's sending out some request to the server. And if there's no file, then everything is fine. It's the users here. Let's focus on the user's privacy regarding its IP address. Okay, I just got a question from Marius. Since I will answer this question during the break. Okay. Yes. And this user, if we can not let's focus on the privacy of the user. And in this context, the user's privacy is connected to the IP address of its device. So it's more like the device IP address. And if there's no firewall, or that you see for all these intermediate routers between the user and the server, they can all see the source IP address and destination IP address. It means all the routers this device is sending out a request to the server or is communicating with this server. And also here, the data itself is in plain text form. It means all the routers in between can see the content of the data. And now you see it's both the confidentiality of the data and also the privacy of this user's device can be seen by all the intermediate routers. So for security, we would like to apply SSL or TLS, this protocol to provide security or like confidentiality and integrity of the data. So then it's like this. The data will be encrypted and the message authentication code will be added. Now in this case, the file won't be able to see the content of the data. None of these routers will be able to see the content of this data, but still they can see the source IP address and destination IP address. So it means the user's privacy in this case is not protected, while the data's confidentiality and integrity is protected. So for users' benefit, then some users would like to hide its source IP address when they visit some web pages. Then how can it be achieved? And I can skip this. Then there are several ways. One is this web proxy. It works like this. I already introduced this before. It's pretty much okay. The source, the destination IP address is not the web server in this context. In fact, it's changed to the proxy's IP address. And then this request, like here, I want to visit this user, wants to visit this web page to fetch this data, then it is sent to the proxy. And the proxy will forward this information, this request to the server with the source IP address as the proxy. And then web server respond this request, and then the proxy server, when to receive it, it will forward this message to the user. In this case, the source IP address is the proxy and destination IP address is the user. So in general, you see the firewall in between the user and the proxy can only see, okay, the destination IP address is the proxy. So it does not know what the real destination IP address in this request. And also from the server side, the server receives this request from the proxy. So the server does not know which is the real source IP address for this request. So in this case, you see the privacy of the user, its IP address, its destination IP address is protected. And we thought the SSL, that still the data can be seen, but it's easy. We add this SSL in this context, then the content of the data will be protected. For this, it seems already it's pretty good. We use a web proxy together with HTTPS, then the user's data and also user's destination IP address, like the user's intention for visiting some web pages already protected. But the problem is that the proxy knows the user's IP address. And mostly people will directly use some free proxy. these proxy servers are not necessarily trustable. And for some sensitive web browsing, then users do not really want to use a proxy because they are not really trustable. Then there's another technique called virtual private network. It's mostly based on signaling techniques. And we will introduce this private network a little bit in depth later on. But there are several technologies that enable VPN. It's the concept is very simple, but the mechanisms and the technical details for different VPN proposals are rather messy. And I will explain only one, this IPSec, is one solution for VPN. The others, it can be done at different layers. We will forget about it. We will skip this in this lecture. The general idea of this VPN is to create a private channel for the user and the VPN server. And also the data will be encrypted, not really based on TLS. It could be based on some other security protocols. Then in this case, we basically replace the proxy by a VPN server. And on the original IP packet from the user, here, let's see, like this, we have the source IP address and destination IP address. Now, this original destination IP address and also the source IP address will be, together with the data, will be encrypted based on the security protocols for VPN. And then the destination IP address will be the VPN server. So the user sent out this request to the VPN server. Then the VPN server will decrypt this original IP packet and then send to the server. You see here, the source IP address will be the VPN server and the destination IP address is the server. So when it receives the response back, then it will encapsulate the data and then send to the user. So in this case, when we have VPN, we don't really need to have HTTPS. It's enough to have HTTP. The only difference here is they use like two different security protection. Like this one, if you use HTTPS while you use VPN, then you have extra layer of security protection. It's pretty good, yeah. Although it's to me, I see it's not really necessary. Yeah. But for most of these VPN solutions, they are in the like layer 3, this transport layer or layer 2. So then it treats the data, either it's encrypted data or it's a plain text, plain form data. Then it treats it as some payload, then it directly encrypts the data. So now everything seems to be perfect. Then if we use a VPN together with HTTP or HTTPS, then the content of the data is well protected. Except that here, the VPN server knows the original destination IP address of the user's request. In some cases, for privacy, the user may want to hide its IP address. then how can the user do it? This comes to the Tor network. This it stands for the Orlean router. So it was designed for anonymous communications in public internet and secure, I would say. The internet has many loads inside, and these loads will be acting as relay loads. And when the Tor browser is initialized, then the computer will select a set of these relay loads as the kind of the routers to forward or to relay its data traffic to the destination. And also there will be like 3 loads that's for performance purpose, and we will see that later. And SSL, this protocol will be used between each relay loads in the Tor network. And it means that for different loads, they use SSL connection for secure communication. And also, yeah, we'll talk about more with the figure in the next slide. In general, this Tor network, yeah, I will, when you see the next slide, it will be clearer. In general, the functionality of the Tor network is to ensure that, so one load, this Tor network load, only loads the previous Tor node and the next Tor node in the path. It doesn't really load the original source and the final destination. And let's see whether I have, yeah. For example, here, it explains what these relay loads or relay mean. Here, relay is like a forward, like when one load receives some IP packet, it will manipulate on this and then forward this IP packet to the next load in the network. So let's see whether it's clear here. Yeah. Okay, let's draw something, then it'll be better. So the Tor network. So we have a user. Then we have, let's say, entry load. Entry load. Then we have load 1, load 2. In fact, it's enough to have, let's say, 2 loads, load 2. And then we have an axis load. Oh, sorry, I forgot to switch the, now you see the, yeah, it's a nice slide. Yeah, of course, it's not made by me. Yeah, I just took a figure from others. And then we have the web server. How it works is the user sent out a request, and the user, in fact, establish a TLS connection with the entry load. So this is a TLS connection. So then the packet will be like this. source IP and then destination IP, and also some it will be the data itself will be encrypted, and this is the source IP is a user. I will just write U, and here I rather load 1, and the destination IP will be load 0, and in fact it is this original source IP and destination. Here it's the server, and here is a user, and this is the data. It will be encrypted. So the this connection, it encapsulates the original request from the user, and with this information, and then the this load 1 will forward this message, this IP packet, to load 1 in the Tor network, and these together will be treated as data. Oops. And it will be encrypted. Then here the source IP is load 0 and destination IP is load 1. And load 1 will forward this IP packet to load 2. Again, the whole IP packet will be treated as the payload of the next IP packet. How did I run? And it will be encrypted with the source IP is load 1 and the destination IP is load 2. And this process will be continued till the exit load. When the exit load receives this, it will then forward to the web server. And here, when load 2 have this, it will keep this destination IP address to the exit load. And then here we have this. Oops. There's a lot of encapsulation in the process. Oops. It's original data, and this is a payload. It will be encrypted, and the source will be the source destination. Source will be exit load, and destination will be the web server. So that when the web server receives it, and it can kind of strip out this out layer encapsulation. Then we see the slide like here. So we have this original message. Then they are, in fact, for performance purpose. Then in this relaying loads, it's enough to have 3 loads: the entry loads in the network, and intermediate load, and then the exit load. Now for the here we have this original message. Then this inter router is the the entry router, and this router B is intermediate router, and router A is the exit router. Then when the exit router receives this packet, then it can decrypt the payload and then send to the destination. And it's like here. So we have the source IP address at destination here in the beginning. It's just a T1. And excuse me, I forgot one important thing. So it encaptures all the loads when the connection is established. So it already has these 3 loads in the place. So then this connection, TLS connection, is already established among these loads. Then this outer layer, in fact, it's the entry layer, the inter layer, the inside layer, it's the exit layer. So it has original data. It encrypted with some keys that based on the protocol by the exit load together with T3 here. And then it has the header that's between the T2 and T3. And also the data itself will be further encrypted. And then it has this header between T1 and T2. And this part will be further encrypted based on the security keys of between T1 and T2. And also the whole will be encrypted based on the security agreed based between user and T1. So when the data is sent to T1, it strips out this head information, get okay, the next load is T2. So then it will send this packet to T2. And based in the initialization process, T1 and T2 already has this secure key exchange process. They know this information. Then T2 will be able to strip out this header and forward the IP packet to T3. When T3 receives it, it will be able to strip out the header information, and also based on the key shared with T2, then it will be able to decrypt the data. And then it forwards to the exit load. This exit load, it will look at the header information, and it's from T3. It will decrypt the data, then find the original IP address, of the destination, that's the server. So it will send out the IP packet with the IP address as a server, and also the original data. Here it's HTTP, but mostly we will use HTTPS, then the data will be encrypted. So in this sense, that the exit load E here only loads the original IP, the original sender is T3, and T3 will only load okay, the next load is exit load, and the previous load is T2. T2 loads the previous load is T1, and the next load is T3. They don't load the other loads involved in this process. For T1, it loads, okay, the original sender is this user, that's the IP address here, but it does not load the original destination IP address because it's encapsulated and secret encrypted in the data here. Then in this process, so T1, the entry loads load the source IP address from the sender, and the exit load loads the destination IP address. And in between all these loads, it has no idea what are the original IP address and what is the original destination IP address. It's pretty much like you have 3 layers of VPN servers. Yeah, it's better to describe it as a web proxy. Yeah, that's better. So you have 3 layers of web proxy, and this web proxy, each of them, it only loads the previous load and the next load. It does not load the original sender and the original destination. You may wonder, okay, what if these web proxy are still not trustable, right? In fact, in the Tor network, I'm not sure whether you use Tor network. Like if I use Tor network, when I open it up, it'll have a bit process of initialization, like here, you see. It takes a few seconds to establish all these loads between the user and the server. And there are only 3 loads involved for performance to reduce the delay. But of course, it can be more. You can configure your Tor network to include more loads in this process. And these loads are in fact randomly chosen in the initialization process. I have attended one Tor network who was one of the designers of this Tor network. He mentioned these loads are updated every second. Oh no, every minute. These loads will be updated in the backend, and also they use a good strategy to randomly choose the loads in the network. Like when I when I open the Tor browser, establish the connection, then my computer itself is also acting as a relay load. If I configure, yeah, I'm willing to be acting as a relay load, then it's possible. Yes, yeah, of course. Now, then you see this process of the Tor network. I consider it's a very useful for protecting users' privacy. And here it's a summary of these techniques. You see, it's pretty much the recap of all previous slides in this table. Then what it can do, you see, for the Tor network, then you can use it to bypass the firewall policy. You can have a network privacy and also the server privacy. And for this log analysis, it's a question mark, and normally it's a free. There's a software installed. Like I installed this Tor browser for this purpose. So in general, it works pretty well for me. And the only disadvantage is that the performance of the Tor browser is not as good as the other solution. That's the issue. Okay, I think let's have a 15-minute break, then we can continue our lecture on network authentication. Okay, welcome back. Let's move on our lecture on network authentications. Well, in fact, authentications are a fundamental solution for security, for both computer security and network security. So let's first take a quick overview of authentication. In general, it's one of the most important mechanisms for access control. Regarding access control, we previously introduced the access control within a local machine, especially it's built in operating systems. But there are other applications that we want to use our device to access some network resources and in some servers. Then in this case, it's not just the access control for local resources in a machine. Instead, it involves the process. A remote device access some resources in a local network. And it's quite important to have proper authentication mechanisms. Then for these two examples, then we may wonder, okay, what are the entity or subjects we want to authenticate? So first, we have this user authentication when a user wants to access the resource in a computer. Or sometimes it's also to access some resources remotely. Another type of authentication, especially for the network, is this entity authentication. So it enables two communicating entities or more communicating entities to verify the other parties and to make sure they are the entities they claim to be. If we look at these two authentication application scenarios, you will see some difference here. And if one user wants to log into a computer locally, then we mostly directly use user authentication. And this type of user authentication can be based on password, can be based on some biometric information, like when we use our iPad or mobiles. And also in some cases, we might use our computers to fetch some resources in a local network, like in the university. Then in this case, this an entity authentication is involved. Then, and also the authentication process is based on the device, not just based on the user. So in general, it's these processes are implemented by some authentication protocols. These protocols are specifically designed for transfer authenticated data between two parties or multiple parties. And it allows the receiving entity, like here, to authenticate the connecting entity, like here. Also, it can be the back and forth. It's like allowing this entity to authenticate this entity. And there are many network authentication protocols. So as I mentioned, they are implemented at different layers of the communication layer stack. So we will just go through some basic ones. and introduce one or two of them. So first of all, we may, before we go to these technical specifications, we may think of what are the types of authentication protocols. There are two general approaches. One is to authenticate based on some secret information. This secret information, then when it is for authentication in a local area network, then we use this secret information-based authentication approach a lot. The first category is called point-to-point protocols. And this by point-to-point, then you have one entity connect to one load, then you have this point-to-point. And there are three types of authentication protocols for point-to-point communications. The first one is this password-based authentication protocol. And the second one is a challenge handshake authentication protocol. And the third one is extensible authentication protocol. For password-based authentication protocol, it's let's look at have some drawing. Point-to-point authentication. This password-based authentication protocol is what we experienced almost every day. Like we have a client and we have a server. So the client sends out the client's credentials. Normally it's a username plus password to the server. And then if this user is in the database of the server who have the access to some resources, then it will like approve the request, or we can say accept. Yeah, approve is fine. Then after that, the client will have some communication with the server. There's a lot more data. So this is how it works. But as you see here, I leave some space for the password. And for security, of course, we don't really directly send the plain text password to the server. In the early days, like Telnet or some other, also this file transfer protocols, and they don't have good security protection on the password. And after a while, it's being improved. And for mostly, like we use a hash for the password, then send to the server. And of course, there will be some minor difference from different applications, but in general, it uses username and then hash for the password sent to the server. Then, if you remember, in the password maintaining database of a local machine, you see already there's one entry in the database. Then the server will check the username, whether the username is in the database or not. If it's already in the database, then it means this client could have the authorization to access some data. And based on this access control list maintained at the server, then the server will decide whether the client is authorized to access some resource or not. This is called password-based access protocol, shortly PAP. And another one is called challenge. Let me see. Challenge handshake protocol. AP. Here, AP stands for Authentication Protocol. In this case, it's so the client connect to the server, and before everything happens, then the server will send a challenge to the client. One challenge. Here, a challenge is normally it's just a randomly generated number or counter. It's some random generated information to the client. Then the client will send back his username plus its password and this challenge. To the server. And the server will check the username in the in its database and also calculate this hash based on its the password of the client. And if it matches, then it means the client is an authorized user. Like that, Google thinks select all pictures with the traffic. Oscar, are you sending a right message here? I don't get your question. Then this is the challenge handshake authentication protocol. Another one, this is what is called extensible authentication protocol, shortly EAP. This one is rather complicated, and now let's look at it. Before that, and also there's another architecture protocol called the 3A protocol based on remote authentication dial-in user service. It's rather long, so I normally just say it's a radius. And it's a very well-designed protocol that was used in local area network a lot. And there are some other protocols. Kerberos itself is complicated, so I decided to skip it. And for public key information-based authentication, then in the beginning of this lecture, we already mentioned for TLS and SSL, it's based on the public key certificate issued by certificate authorities. And for PGP, we didn't really discuss a lot on how its public key certificate is managed, but it's like an informal way of providing sufficient trust among communication parties based on informal signatures on the public key certificate. In general, this type of authentication is based on public key certificate. Then it's mostly used for the internet because it's not easy to have secret information shared between parties in the internet. So it's it's plausible to have for these two types of authentication. Select all pictures with the traffic lights. I see, Oscar. This type of mechanism, it's not for handshake, this protocol. Instead, it's for preventing like denial of service attack. So it's to prevent like botnets to log in or register at some websites. Then they use some pictures or there's some other type of this code to prevent some automatic registration or sign up at some web servers to restrict the access from botnets. That's not really the handshake authentication protocol. Now let's look at one typical local area network authentication protocol. It's called IEEE 802.1x. This is a general figure of this protocol, and it uses extended authentication protocols over LAN. So it's also has can be termed as EAPOL. And basically, you see now let's look at this figure. So a user or a device in this network, it wants to fetch some resources in the local area network or maybe in the internet. And then the user sends out some like authentication information to the authenticator. Here, this authenticator, mostly it's the wireless access point. And then this authenticator will forward this message to the authentication server and based on another type of protocol. And here it's mostly they use this radius, this authentication protocol to authenticate the users. If the user provides correct information, either it's a password-based or it's a challenge handshake protocol. If everything, all the information provided by this supplicant is correct, then this authentication server will make a decision that this user should be given or should be rejected for the request for some services or resources in the network here. So if everything works fine, if this user or this device is authenticated, then the user will be forwarded, the request will be forwarded to the network here. Then we will talk more about it. So this is a progression of this process. And we have three components here. They use different terms from different protocols. This is rather annoying, but let's see, okay, this is the user device. This is this authenticator's device, like wireless access point. And this is the backend authentication server. Mostly in many organizations, they separate these two parts, but in some small organizations, they may have these two together. In general, like if we hold an iPhone or like an iPad, then we want to connect to the server, especially in the university, we have this ED room. Then we want to establish a new connection. And first, this device will ask the supplicant to provide its identity. And this is a request. Then this is EAP message. Then also this, after that, the supplicant will provide this identity. The authenticator here, it acts as a proxy for the authentication purpose. So itself, especially in this context, will not verify or check information. And in fact, it will forward the information to the authentication server. The authentication server will check this identity of the supplicant, and sometimes based on whether it uses the PAP or whether it is a CHAP protocol, it might ask for some challenge or generate some challenge to the authenticator. This authenticator, again, as I mentioned, it acts as a proxy. It will forward this request to the supplicant. The supplicant will be responding some message based on this request. And then this response will be forwarded to this authentication server. Then if the response is authorized by this authentication server, then here the Radius server will send this accept message to authenticator. Then the authenticator will forward this message to the supplicant. Then basically, then it's access. After this, the supplicant will be able to access the network resources via the authenticator here. Now, in this case, what are these extensible authentication protocols, this EAP? It's not a single protocol. Unfortunately, it's an authentication framework. It's not specific authentication mechanisms. So it provides this architecture for different purpose, for different authentication protocols. And here we have these 3 layers. It's more like this architecture. And for the access, then it might be this P2P or protocol, and it might be this cable internet connection, or it might be Wi-Fi internet connection or other internet connection that the device used to connect to the local area network. Then this for authentication, then it has this IEEE 802.11.1x, this one in the place, and it will forward the message to this extensible authentication protocols. That's this authentication server in the previous slides. Then the server will based on different protocols, like here, this EAP based on TLS. You already know TLS. This is EAP based on tunneled TLS. And this is a pre-shared key. There are a lot of others. So you see here, it's approximately 40 authentication protocols to be used by this EAP. In general, as we have mentioned in the iPad screen, that it's there's a point-to-point authentication. At least it's look like a point, like one device supplicant to authenticate itself by the authentication server. Then again, in this here, this EAP, this extensible authentication protocol, it's a peer authenticator and the server. So we have a different term from this 802.1x, but in general, it's this is a device, this is a wireless access point, and this is remote server, like the authentication server. So we have this message, like this client computer, then authenticator. Here is this access point. It's not necessarily always this wireless access point. It could be this keyboard connection. And then this authentication server is a backend server that negotiates the use of what are the EAP method to be used with this EAP peer, and then validate the peer's credential. And after that, they decide whether this peer is authorized or not to access the services in the network. All this traffic is encapsulated by this what is so-called EAP messages. There are some extra information. I skip this. This is you see a lot of similarities from here, EAP message flow, and also the very beginning, this one. In fact, they are quite similar. Again, this EAP peer, like when it asks for authentication, then this authenticator will request the identity, then respond, and the authentication does not authenticate this request. Instead, it just forward to the authentication server. And there might be several steps of this authentication process. In the end, it will decide, this authentication server will decide whether this request is successful or is a failure. Now, what this Radius server? It's 3A protocols manage the network access. So this Radius acts as the authentication server in most of the local area network. This 3A stands for authentication, authorization, and accounting. So that's why I mentioned in some cases, the peer could be authenticated, but maybe there's some policy in this authentication server which determines that this peer is not really authorized to access some resource. So there will be an access control list maintained by this server. When a peer is requesting some resource, and then this server will check the access policy and then decide whether the access should be given or not. I can. And how it is this authentication flow, then it might use this PAP, this password-based authentication protocol, or it might use a challenger handshake authentication protocol. The decision is reject, accept, or maybe send new challenge, more challenge to verify whether the peer is authorized or not. I have, here, I forgot to include one figure that maybe it's, it explains better. This one. Yeah, this one. So I will add this figure again in the slides. So this is how it works. This XO0.1x. So when this authentication server approves this authentication process by the supplicant, then this here's a port controlled by this wireless access point. Then it will be switched on. Then the supplicant will be able to access the resource here. It could be the local network resource. It could be just the normal internet via this wireless access point. And before this supplicant is authenticated, this port will be switched off. That's by default, it's switched off. If the supplicant is authenticated, then this port here, the switch, will be switched on. There's this radius roaming. That's like the ED-ROAM. I mean, we all use ED-ROAM. If you are in the airport or if you travel somewhere else, then you use ED-ROAM, and you just need to provide your university's credential. Then you will be given the network access, right? How it works, it's like another radio server behind and connected via the internet. So suppose you are at the airport in Stavanger, then you use a device to connect the wireless access point, and there's one network for the ED-ROAM. Then you will be asked to provide your credential for the ED-ROAM account. Then since you are a student from the University of Bergen, then you provide the University of Bergen's credential, and then it will forward, like send to this radio server, and the radio server checked, okay, this is in Stavanger, they check, okay, this is not in my domain. It's not, I'm not responsible for this request, but I know in my realm, there's other radio servers, like from the University of Bergen, from University of Oslo, or like from NTNU. Then this radio server will forward this request to the destination server based on its domain. So then we use the university's credential with the uib.no. Then it will forward the request to the specific domain of the radio server. Then the radio server will, check the information and approve the connection. Then it will send it to the radio server. Okay, I approve that this user credential is within my database, so please give access to this user. Then it will forward this approval to the access point, and in the end, this device will be able to get the network resources. That's how it works. So in the end, let's look at the virtual private network. I think most of you have used a VPN. So the intention for this VPN is to allow remote users, especially for some big organizations, like they have branch offices, to access corporate applications and resources. That's the major purpose, to enable the user that they can access their organization's resource as they are staying in the office. That's the purpose. How it works, it is realized based on what is called the VPN tunnel. In essence, a VPN uses encryption and authentication in a lower protocol layers. That's why, like, if we configure the VPN beforehand, then we just click VPN and then we got connected. Like here, I also have this VPN connection configuration. Then I just connect VPN. Then I will be able to access the university's resource from my home. And these are lower protocol layers. It's relatively transparent to the users. But its general goal is to enable users to transfer data across public networks in the internet as if they were directly connected to the private network based on the tunneling techniques. So it provides benefits that a remote end system can function as they are staying in the network directly. And regarding the implementation of these VPNs, as I mentioned, there are quite a lot of techniques. But most of them, they are based on the tunneling techniques. This tunneling is a communication, sorry about this typo, a communication protocol which allows the movement of data from one network to another. and it involves the allowing private network communication to be sent across a public network through this encapsulation process. Like here, to convince you that VPN is rather complicated, you see here, these are the classification of VPN techniques. It can be realized by different techniques. You see this, it can be realized based on layer 1 APN, layer 2 APN, even layer 3 VPNs. Layer 1 is a physical layer, layer 2 is a data link layer, layer 3 is this network layer. And this is based on the layers, and also based on whether it's a customer provision or whether it's a private provision. It can have different classifications. There are a lot, and we will just look at this IPSec. This is one technique that enables VPN at the internet layer, this layer 3. So what this IPSec tunneling is, we have this host, and suppose we have many routers in the middle in the internet, and this host could be the server of an enterprise. Then they have the neutral network. Suppose I'm sending some traffic to the internet via the VPN of the university. Then here in my home network, I directly connect to the router, and then this information will be sent through the internet. And if I'm accessing my emails, or like I want to download some papers, then I have to use a university network with subscriptions. Then I have to use the virtual network. Now how it works is this whole process, my computer and the university server, or especially this VPN server, all the traffic between this host and the server will be encrypted within an encapsulation of this tunneling. Then for the intermediate, these routers and my home routers and the internet and some routers in the university network, they are not able to see the content in the tunnel. This tunneling is encrypted. The data in the tunnel is encrypted. How is this process? It's like if I send an IP packet, right? At the application layer, you have the data, and then normally we add this TCP header, and then at the IP layer, we had the original IP header. But before this is sent out to this router or local internet, with this IPSec, you see here, it will take this whole information as a payload, and based on its authentication protocol, it will use this, it will add this authentication, that's the message authentication code, and this some tail information and also some head information. So with this authentication code, the integrity of the information is protected. Then after that, it will also have this encryption process. It's like here, there's a grayed out area. It's encrypted, and this ES authentication is for the whole message. Then all of them will be treated as the payload of a new IP packet. Then here, a new IP header, like the source IP address and destination IP address, will be added here. Then all the intermediate routers in the middle they can only see, okay, this host is sending out some request to this VPN server. So the destination IP address will be the VPN server. The content of the data won't be seen by all the routers here. That's the advantage of VPN. I remember one of you asked me like this VPN, and I consider the biggest advantage for end users is when you travel, you use some public internet, but you have to maybe log into email, you have to log into your online bank for some emergency situation. Then in this case, it's not secure to directly log in via this public access point. Then it's better to connect to VPN, and after that, all your traffic between you, your computer, and the VPN server will be encrypted, so the access point at the airport, at a restaurant, won't be able to see the data inside in the tunnel. So that's the biggest advantage. Okay, I think then we must stop here. That's pretty much what I'm gonna introduce about this VPN and IPSec.